Okay, so we talked about vaporization, which is evaporation and boiling. We're going to talk about the other really common phase change, which is solidification, and the opposite of solidification, unsolidification. No, freezing and melting. And you know that we can write the Le Chatelier's equation like this. A solid plus heat yields a liquid and vice versa. And that's pretty self-explanatory. We will look at phase change diagrams in a little bit, which always show up on the ACT. The molar heat of fusion is the thing that I want to talk about. You all know what freezing is. It happens where the solid and liquid states are at equilibrium. So same as boiling happens at the state where the vapor and liquid are at equilibrium. Molar heat of fusion is how much energy it takes to melt 1 mole of a solid. So how much energy it takes to melt a block of ice with 1 mole. So 18.02 grams. 18.02 grams of water in the solid phase is 1 mole of water. An 18.02 gram ice cube. The amount of energy that it takes to convert all of that to a liquid is the molar heat of fusion. This is a similar situation with the molar heat of vaporization. Something that requires more energy to melt it has, this is a choice, stronger or weaker internal bonds. Stronger internal bonds. So if we think about substances like wax or water that are pretty easy to melt versus substances that are really hard to melt, like steel, diamonds, salt is hard to melt. You tried melting it in a lab in here. Those things that are hard to melt have much higher forces of internal attraction. Have you ever had ice cubes magically disappear in the freezer? I know at least one of you mentioned this. Ice cubes, you put them in the freezer, you leave them there for a few years, and they're gone.
A few years?
Sure. That's sublimation. So we can have water that goes from a solid directly to a gas. Never enters the liquid phase in the middle. That is called sublimation. Something sublimes. You messed with a substance in your first lab that sublimed. Remember where you burned off, was it ammonium chloride, I think? You had a physical mixture to separate, and you heated the stuff under the fume hood, and it produced a lot of fumes. That was subliming. It didn't turn into a liquid. It didn't melt first. It went directly from a solid to a vapor. That's sublimation. Deposition is exactly the opposite. That's where a vapor goes directly to a solid. Can you think of an example of deposition that you see very often in the morning? Frost. Yeah, a frost is deposition. You've got water vapor in the air that goes directly to a solid ice crystal on substances. It doesn't turn into a liquid first. It doesn't condense and freeze. It just deposits. This tends to be something we really only see at very low temperatures or low pressures. So it's, pardon? Yeah, for both, sublimation and deposition. Both really tend to occur at low temperatures, low pressures. The inside of your freezer is low temperature, though it's normal atmospheric pressure. Outside on a winter morning is, again, low temperature, the normal atmospheric pressure. We can replicate those conditions with very low pressures. Okay, so now let's look at, we've talked about all the phase changes. So let's look at making sure we can name all of them and locate them correctly. Okay, so we've got the two changes that occur between solid and liquid form. Solid to a liquid, melting, liquid to a solid, freezing. Now, what if we go from liquid to a gas? That's vaporization, but there are two distinct forms of vaporization. What are they called? Evaporation and boiling. What if we go from a gas to a liquid? Okay, so now what if we go straight from a gas to a solid bypassing the liquid phase? What do we call that? Deposition. And if we go straight from a solid to a gas, we call that what? Sublimation. Okay, that summarizes our phase changes. It's important to note, and I think this is something students very often get confused about, any substance can exist in any one of these three phases. Any substance can exist as a solid, a liquid, or gas. Any substance can go through these phase changes, from water to oxygen to steel. So can we have liquid oxygen? Yes. What does it require? Specific conditions of pressure and temperature. Could we have solid oxygen? Yeah, theoretically. It would require incredibly low temperatures and incredibly high pressures. Can we have liquid steel? Yes, of course, we can melt steel. Can you have gaseous steel? Can you vaporize steel? Yes. Incredibly high temperature, incredibly low pressure. So it's all about pressure and temperature. That leads us into phase change diagrams. Okay, so this is a phase change diagram. This is straight out of your notes. And remember how we said any substance can exist in any of those phases? It's all about pressure and temperature. The phase change diagram shows the relationship between temperature, pressure, and state. So we can look at a phase change diagram. This happens to be a phase change diagram for H2O. And if we look at it, we see that this region, so temperatures below 0 Celsius and a pretty wide range of pressure, it exists as a solid. Temperatures above 0, and again a pretty wide range of pressure, this whole region, it exists as liquid water. And in this whole region down here, it exists as water vapor. That, you can make a phase change diagram for any material. And we're going to talk about a few important points on the phase change diagram. I want to talk, about equilibrium, or the triple point, which is right there. And the triple point is where all of those lines meet. The triple point is a really kind of unique condition because it is the temperature and pressure conditions under which you can have all three phases of that substance in equilibrium. So you could have a closed vessel with water vapor, and ice in it, and at the conditions specified by the triple point, you can have water molecules leaving liquid phase becoming solid water molecules leaving solid phase becoming liquid, and exchange occurring between gas and liquid as well. All three of them going on at equilibrium. The ice isn't melting, the whole thing isn't freezing, the water isn't vaporizing, the vapor isn't condensing, it's all in equilibrium. It's a pretty fleeting little point. It's hard to nail something on its triple point, but you can, and it's an important thing to know. If we follow the line, and let me enlarge this. If we follow the line at standard pressure over to here, what temperature does this meet up with? What is it? So you can look on the graph. 100 Celsius, which is the what point of water? Boiling point. That's the boiling point of water. And that's exactly what we would expect. At standard pressure, water at 100 degrees is going to go from liquid to vapor. If we're climbing up to 100, it's going to start to transition over to vapor. If we're dropping from some higher temperature, as we get to 100 and drop below it, it's going to start to do what? What's the process called? Condense. Yeah, it's going to start to condense from a vapor into a liquid. You can really, the phase diagrams are not difficult to understand, but they do show up repeatedly on the ACT, so you want to get familiar with them, and we'll do a little bit more work with them later. I will give you a quiz question or two tomorrow with phase change diagrams. Questions, comments, concerns on them? Okay, so what we've got is, okay, so if you look at this phase change diagram, you have a critical temperature. And for the substance shown here, and I don't know what this substance is, the critical temperature is 374 degrees Celsius. Above critical temperature, it does not matter how much pressure you put this thing under. You cannot force it back into a liquid phase. Okay? So if you notice, the line for liquid just ends there. And above that point, everything else is vapor. You can't force those molecules back together as a liquid above that critical temperature. So for this, it's 374 Celsius. The critical pressure is the point where that cutoff line starts. And so we call this spot right there the critical point. Phase change diagrams, really handy. You can look at a broad range of conditions. You can predict the phase something's going to be in. They will be on the ACT and they will be on your test and your quiz tomorrow. So, questions, comments, concerns about phase change, critical pressure?